Hello everyone and welcome to the second video lecture on vibrations of beams. In this lecture I'm going to discuss with you the equilibrium analysis that can also be performed by simplifying the equation of motion to the equation of equilibrium. So it's not so much about vibrations actually, but I think it's very nice to demonstrate that the equations of motion of these continuous systems actually also embody, they contain static solutions as soon as we simplify them. So I'm going to look at this clamped free beam subjected to a moment at its tip. And maybe you know from previous lectures in mechanics that this is a problem of pure bending. Maybe you remember the solution. But we will find out this now using our dynamic skills rather than this dedicated techniques you have learned in mechanics classes before. So for that I will simplify the equation of motion to the equation of equilibrium, where over here v was a function of x and t, and I will simplify it now by dropping the time dependency. It's a static problem, nothing changes in time. So the first term drops, and this becomes just regular derivatives of v with respect to x, and f also only depends on x. So if we divide this equation by EI, we just have a fourth order trivial differential equation for v. The general solution for v can be obtained by integrating 4 times. Now let me write this down as follows. Maybe if you are a mathematician you don't really like this notation, but I think it will be clear anyway. So f divided by EI and then dx 4 times. So this means integrating this 4 times. Doing this, there will, each time we integrate we get an integration constant. So there will be 4 integration constants. So here we will have something that looks like c1x to the power 3 plus c2x to the power 2 plus c3x plus c4. The fact that there are 4 integration constants means that we also need 4 boundary conditions. So this is also, the fact that it's 4th order in space means there will be 4 boundary conditions, and there will be a 2 at axis 0 and 2 at axis L, where axis 0 is over here and axis L is over here. So let's try to find these boundary conditions. Well, at the location of the clamping, the deflection is suppressed. The beam cannot move there. So that means that V at 0 must be 0. Moreover, as this beam is going to deform, maybe it's going to look like this, the slope will be 0 here. Now the slope, let's call that theta at 0. That is actually the derivative of v with respect to x at 0, which must be 0. Then at the free end, there is no force. If we would make a small free body diagram of this tiny end, let's do that. Let's so. Then as on this side we have this external moment. Now following the sign convention, here we have a shear force S at L and an internal moment M at L. Okay, so from this free body diagram we can see what the other 2 boundary conditions are. We cannot say anything about V nor of the slope. They will be non-zero and still need to be solved. But at least we know that the shear force S at L is equal to 0, and that the bending moment at L equals this externally applied bending moment. So how can we express this S and M, these boundary conditions, in terms of something with V? Well, for that, recall that M equals EI times the second derivative of v. So this is EI times the second derivative of v evaluated at L. Also recall that S is the derivative of M. So that means that S is actually EI times the third derivative of v with respect to x evaluated at L. So these are the four boundary conditions. Let's apply them and see what C1 to C4 are. Let's start with the first one by demanding that v is 0 at 0. Let's first establish that there is no external distributed force in this case. So that means that this first integral is 0. F is 0. So if we then substitute that v is 0 at 0, we are left with C4, right? So C4 is equal to 0. That's nice. Then for the derivative, if we differentiate once, and evaluate at 0, we are left with C3. So from the second boundary condition, it follows that C3 is 0. So that is good. Let me maybe with red indicate that these terms are already out. So we are left with C1 and C3. Then for the third boundary condition, we need the third derivative. So if we differentiate once, we get 3c1x squared. Another time we get 2 times 3, that's 6c1x. Another time it's 6c1. So this is in fact 6ei times c1. So that means that c1 is 0 as well. A lot of these coefficients are 0 for this example. And then finally for c2, we get 2ei times c2 if we differentiate this. From this we can solve that c2 equals m divided by 2ei, right? And then all the coefficients are solved. So maybe here c1 is 0. And that means that the solution for this problem is that, so the solution is in fact a parabola that v as a function of x equals m divided by 2ei times x squared. So that means that this shape will indeed in deflected form be some kind of a parabola. Okay, so I don't think a lot of new stuff has been said in this lecture. Maybe if you didn't take any classes on mechanics before, it is new, but I hope that it is clear how to get from this equation of motion to the equation of equilibrium, and that we need 4 boundary conditions in these kind of problems. That will also be the case when we turn our attention to dynamics again. So that concludes this lecture. Thank you for watching, and let's do some dynamics again in the next lecture. See you there.